Hello class, and welcome to the lecture on arrays. So today we're going to be discussing arrays, which are a very fundamental data structure. It's kind of the basis of computer science here. A lot of the examples that you'll see in some of your more advanced classes will, such as data structures and algorithms, will, for the algorithms portion anyways, show the example, in terms of arrays. So we'll go ahead and jump right in here. So an array is a data structure. It's a linear data structure that stores a collection of data elements. Now, what we mean by data elements, we could be talking primitives, such as, integers, floating point values, characters. Basically, what we mean by primitives are anything that is not composed of a smaller building block, at least, in terms of the programming language anyways. Behind the scenes, of course, there are exceptions. So everything's going to be of the same type in an array. You can have arrays of integers, like I said, arrays of floating points, arrays of objects, which are a user-defined data type, which classes instantiate objects, and you'll study classes in object-oriented programming, but they are made of smaller building blocks. So the point is, array holds collections of stuff. It's a linear data structure, holds collections of stuff. Now, here's a good point. Why do we need arrays? Well, okay, we'll go ahead and show you why you need arrays. Let's say we want to store, 10 grades, or let's say we want to manipulate 10 grades. I can do it one of two ways. Let's say I'm going to perform some operations on these. All right. Let's say I want some class averages. Grade 2. Okay, I can tell you right now, I'm already tired of typing. All right, we'll just stop at 5. I'm getting lazy here. So let's say we want, we want a class average. Okay, so if I wanted to find some sort of function to get the average, all right, I know that I have 5 grades here, so I'll go ahead and say, int grade 1, int grade 2, int grade 3. Oh man, this is kind of a nightmare here. Okay, and what I'll say is right, because this is kind of the definition of average, the sum divided by the number of elements that you're averaging. Wow, okay, so there are a few problems here. I had to type a whole lot of stuff. I had to define 5 grades. I had to, and of course I can abbreviate this a little bit by doing something like this, defining them in a row, but that still doesn't save me all that typing and all that work. Here, same. I got a whole bunch of arguments. I had a whole bunch of stuff here. What if my number of grades could vary? My class may not be, I think the EWF class limit is 30 for online classes generally. What if people have dropped? What if I had 26 people that I want to grade? Gosh, 32. What if, what if some overrides have been made, some exceptions have been made? So you see the problem's kind of inherent here in just performing operations on the primitives themselves, or even objects themselves. So this is why collections can be interesting and important to us. Now, if I want to come back, let's say I can store these any way I want. That provides me more freedom, flexibility. It's going to be a lot easier. I can say something like an array. An array of grades. Okay, so there's 5. I can even expand this out. Who cares, at this point. There we go. So now I've got 10 grades. And I'll explain what I'm doing here shortly if you haven't read the chapter yet. But anyways, I'm showing you how flexible this can be. There we go, voila. So this way, what I've done here, and I can just call this this auxiliary function this way, grades. And if we want, we can define a constant named size, and here we'll just say int size. Doesn't really need to be a constant. So there we go. There's my average program done. Now, first of all, I didn't have to type a million different things. And second of all, it's very flexible, right? So my array can change in size. All I have to do is change size here, here, or preferably if I made it a constant, up here I could declare it to be a constant, and that way I could only, I could change the constant at the top once. So this is, kind of flexible and powerful. All right, and this is just a very, very small example of what we can do with arrays. Arrays are a very fundamental, very important data structure. So yeah, this illustrates what I said. Imagine keeping track of, well, heck, I did five test scores, or 100 or 1,000. You'd have to name all these things. You'd have to manipulate them individually. It becomes impossible. This is why data structures and collections are very important. So here you see array declaration. You declare the data type, and the name, and you have your open and close brackets after it. Now, the number that appears between the open and close brackets is the size of the array. That's how many, in this case integers, that's how many elements, integer elements we are storing. Now, something important to note, always remember this, you'll mess up a lot and it'll kind of be hammered into your head because you'll mess up enough. Array indexes start at 0. So when you see an integer array of 5 elements, just know that those array addresses, the subscripts, are addressable from 0 to 4. Position 0 is the first element in the array. Position 1 is the second element in the array, and so forth until 4. So score 5, if you were to try to address the 5th element, if you were to say, score 5, that's not valid. That's not part of that array. It addresses the area of the memory, area of memory past the array. All right. So this is your index into the array, and yes, you also see it referred to as a subscript. So watch this. Java will keep you from shooting yourself in the foot. If you do this in Java, and some other languages too, they will somewhat, I don't want to say they'll do bounds checking for you, but they will throw an exception. Watch this. We'll declare an array of 3 ints, and then we'll assign a value to something far outside of the array bounds. So if we declare an integer, a 3-element integer array, we should only be able to address my array 0, my array 1, and my array 2, correct? Because we have an offset of 1. So what I'll do, I'll create something way outside of those array bounds, all right? And let's see what happens. Row. Okay, so you see the problem. It didn't grab at me. Watch this. Okay, well, yeah. So you see it is possible that we can write to the area memory behind the array. It is also possible that we can't create a segmentation fault. Anything can happen here. If we overstep the bounds allotted to the program, then the operating system can terminate our program immediately. I bet this says app crash. Yes, app crash. So it's really unpredictable behavior. However, the compiler does not see this necessarily as an error. Watch this. That's definitely, even my array 3 would be incorrect. That would be overstepping the bounds of the array. Yeah, see, so we get a garbage. This looks like, some sort of memory location kind of. We can get garbage there. And it's not an error. In Java, if you do this, you'll get an array index out of bounds exception. In C++, not necessarily, usually won't. All right, so array variables. Yes, these are, you'll hear them mainly as elements, but you can be heard. They can be referred to as index variables or subscripted variables, and they're what make up the array. They are the individual elements of the array. Okay, as I said, your indexing starts at 0, goes up to the size of your index minus 1. Just remember that. And again, if you forget it, no biggie. You'll shoot yourself in the foot, you'll spend some time, and then you'll figure out what you did wrong, and you'll remember it. Array variables can be any type, however, they must be homogeneous. Okay, arrays must contain elements of only the same type. Yep, all are of the same type. So you can have, like I said, arrays of any kind of type, int, double, float, whatever you want. They all have to be of the same type, however. Okay, and you can index a variable, all right? You can index a variable. You see what I did here, see out my array. So what this does, so I have an integer array made up of 3 integers. And if I do this, what this is saying is display this first integer. So this expression right here, my array subscript 0, evaluates to an integer value. And that is the first integer, of course, of the array. So if I do something like this, it's going to display 3 here, right? Since 0 is the first address here of the array. Well, it's the first element of the array. Yes, 3. So as I showed you, within the brackets is the size of the array. Then when you index into the array, you just use the array name and the index within brackets. So this here would be the 4th element of the array score, of the integer array score. So this would evaluate to an integer value, the 4th integer in the array. And again, starts at 0, and we'll go to the size of the array minus 1, since your offset is 1. Okay. And yes, you can assign values to array elements. And we'll see an example of this. We'll do an example here right now. So we saw that it was 3. Now what I can do is say, my array 0, I can just say plus plus. All this does, plus plus, it will add 1. It's the shortcut increment increment operator, it will add 1 to this first value of my array, or this first element of my array, which is 3. So it will result in 4. So now, instead of 3, here I should see 4. Let's go ahead and compile and run. Yep, voila. So we can manipulate them directly. Or, in this case, score and +1. And, you don't have to use literals in here. As you can see here, you can use variables. All right. N is 2, and +1 evaluates to 3. So for this basically assigns the value of 99 to the 4th value of score, that is score subscript 3, 0, 1, 2, 3. All right, this is where kind of arrays really shine. We saw how easy it is to manipulate arrays and loops. If I want to do something with my array here, how about this? How about I assign successive values from 0 to 10. Well, no, let's just say from 1 to 10 to the elements of my array. All I have to do remember, I said we can use a variable to index into the array. You know what, we'll do this. All right, let me make sure I did this right here. So I declare an integer array of 10 elements. Then for values 1 through 10, I assign the value to the corresponding place in my array, to the corresponding index in my array. You know what? I forget that we're offsetting by 1. Okay. Let's let it rip and see what we got. Dot operation type instant care. Just a moment. Oh. You probably saw that before I did. There we go. All right. So you see what we got going on. I assign the values 1 through 10 to my array 0 through 9. Remember, it's only 10 elements, so we have to start at 0 and go up to 9. And then I display them. So loops are very, very, very useful in processing arrays. Again, as you saw earlier, what I can do is I can even create a function which takes a size, an integer size argument representing the size of the array, and then we don't have to hard code any loops or any kind of processing we do. So it becomes a lot more flexible. We can use arrays of different sizes. So yeah, and you see here they are hard coding, just like I just did. We haven't gotten, we haven't really discussed size operators yet. But yeah, here you start at 0, go up to size -1. If you want to step through the whole array, and then you perform whatever operations on the array you want. In this case, what they're doing is it looks like they are calculating the difference between a max score and the actual score represented by the integer in the array here. You can look at display 7.1 to figure that one out, but should be able to understand. Yeah, like I said, it's kind of preferable to use a constant. That way, if we use the same, variable for several things and it's always of the same value, it's better to use a constant. That way, if anything changes, let's say some magic number, some size of something in a program that we always use, we don't have to go hunting for all occurrences of that variable. We may miss some. We can change it in just one place at the very top. Remember, we declare constants at the top of a program. So we could do something like this. But we have number of students. Well, it doesn't matter. We could say. And that way we don't have to go redefining size variable each time. It's not a size, it's a constant. And the beauty is we can't change it. We can't change it elsewhere in the program. That would make things very difficult to debug. When you have a constant and you try to change it inside the program, the compiler will bust you. All right. So yeah, this is true. Using a variable to declare the size of an array is not going to work. You can't generally, see out, enter the size of the array, cin, an int, and use that int as the size of the array. You can't do that. You can use dynamic arrays. You can use pointers to define array sizes that way, and that's a little more advanced topic. I think we discussed pointers in Chapter 9, so that's going to be a separate class. So yeah, the syntax again. What we did is said int myArray 5, and you see all that is the data type, the array name, and the array size. That's it. Then again, starts at 0, goes up to max, size -1. So like I said, arrays are linear. They're contiguous. They take up contiguous blocks of memory. So the first element of an array is stored at the base address of the array. So an array is stored at a location, and each element is stored next to the previous element from 0 up to the size of the array. Okay, consecutive bytes. Memory is represented by bytes, rather. It's going to be consecutive memory locations. And here we have an example, declaring an integer array named A of size 6. And yes, stored one after another, like I said, contiguous in memory. And the address of A0 is, like I said, is known as the address of the array. And that's how we when you index into an array, what the compiler does is it takes the first element of A, and then it will add the offset, in this case 3. So it will add 3 times the size of whatever you're storing. Remember, integers can be 4 bytes, 8 bytes. So in this case, it's compiler dependent, but the address of A3 might be the base address of array of A, plus 3 times, 4, which would be 12, or 3 times 8, which would be 24, depending on the compiler and the, the system. Out of range, like I said, you will get array index out of bounds. Exceptions in Java, if you overrun arrays, you'll get runtime exceptions, really. That's it. You won't get compiler exceptions, or you won't get compiler warnings or errors. You will not in C++ generally. You'll just get some trash, whatever is in that memory location that you that you step over the array into is what you'll get. Yep, note, it does not produce an error message. Do not, should be does not. And as we saw, you can get any kind of trash if you overstep those bounds. So remember, if an array is of size 6, the most you can index in there is 0 through 5. A5 is the max index you can have. So A7 is definitely stepping over the bounds of the array by 2 times the size of that element in bytes past the end of the array. Yep. So yes, you can clobber other variables. If there's some other variable in memory stored next to this, next to the array, which is generally, they're kind of they're stored on boundaries, but generally they're somewhat contiguous. You can clobber other variables, overwrite other variables, and so you can have real problems. And as you saw, you can explicitly define values in arrays, which is what I did here. Well, actually, no, it's what I did previously. Yeah, as you see, you can, this here is optional. You can say int children of size 3, an array named children of 3 integers is going to consist of these values. This 3 should be optional. We can take this code throw this in here. This will definitely compile. All right, and so should this here. If I'm declaring it to be of 3 elements, I don't, it's going to assume that the size of the array is 3. Should, anyways. Let's make sure here. Sometimes you never know that some things are compiler dependent. Yes. Default values. So you see here, they do declare size of 10. However, they only give it 2 values. So what the compiler is going to assume is that int a subscript 0, the first element, the first integer in a is going to be 5. So is the second one, the subscript 1. Then, you'll generally the rest will be assigned the value, if it's integer 0, if it's Boolean, false, whatever the default values are. Yeah, so if no values are listed in the declaration, usually you'll get a default. You get zeros, you'll get, false if Boolean, if, double, you get 0.0. However, this depends on the compiler. Don't count on that. Now, this is pretty interesting. The C++, the 2011 standard, does allow for, it's an iterator. In Java, this is what we call iterators, and this is very handy for collections. Java will let you do this for all collections. You see for, int I in my array, then blah, blah, blah. This is very handy. This way we are guaranteed to never overrun the bounds of an array. Okay? If we want to display arrays, we can do a lot of things with this here. But this way you will never, oops, sorry. Now, for C++ for 2011, you'll have to specify that standard. Okay, so don't be surprised when this doesn't compile without jumping through hoops here. All right, and so here we have an example. We have an array defined to be composed of values 2, 4, 6, and 8. And then, you see here for each integer, and, we will assign that particular integer a value of x because it's going to return an integer for each integer in the array. For each integer to x in the array ARR, we will display it. Okay? So this, will indeed It's actually not going to output 2468 because I don't see a space there. I say it's going to output 2468. Okay, because we don't have any spaces in there. So that's going to be the output from here. All right. So here you see we just have, A4 and int A5. Well, when you saw int, something should have clicked in your head here, and you should have said, okay, this is a declaration. Declares an integer array named A composed of 5 integers. And then this is just an indexing into the array. So this is saying the 5th element of integer, subscript 4, because 0, 1, 2, 3, then 4, right? So show the output of, here we have a character array consisting of A, B, and C. And for 0, 1, and 2, we simply index into the array in the corresponding integer 0, 1, and 2. So this should output A, B, and C. And you should run these, or you should run this one, and you should use this one in context, just so that you get it. All right, so we're using arrays and functions. We can pass arrays. We can even return arrays, although we won't be discussing returning arrays yet. All right, so here you have three declarations. Excuse me, you have a couple declarations. So you have an integer I, you have an integer n, and then you have an integer array of 10 elements. Okay. And I just have some garbage here. You're just declaring there's a declaration of the void function, which means it doesn't return a value that takes the integer value n. So for A10, you know that you have elements 0 to 9 that you can address. Okay. So yes, you can, like I said, you can index these and they will return integers. So these 3 are all valid, assuming that, I is a valid integer, which it is, presumably, since we declared it up here. So these will return integer values. They will pass these integer values to the myFunction function. Okay, now arrays themselves as function arguments. You can pass an array. Okay, an array is generally passed by reference, not by value. Arrays can be huge, so we don't want to pass a zillion elements to a function. Okay, that would require a lot of memory overhead. Imagine we have an array of 1 million elements. I don't know. That could be too much memory. We might overrun the stack. We might have stack overflow. We could run out of memory. So just think of them as reference calls, okay? Because basically what is passed is the address of the array. Remember, the address of the array is the same as element 0 of the array, the index 0 of the array. So here is a function declaration which takes an array as an argument. So we have, it doesn't return anything, it's a return type void. It's called fill up, and it takes an integer array. Of course, the name of the int doesn't, in the declaration it doesn't matter, but it takes an integer array. And, as I said, remember, it's a best practice to include an integer representing the size of the array so that you do not overrun the array bounds, and so that you can use it, easily in loops and for processing, because that way you can have arrays of different sizes that you pass, and you aren't tied to a particular array size, a fixed array size. All right, so here's our previous declaration. Then, if we declare an integer array named score, of 5 integers, and so number of scores is, of course, going to be the size of that array. That's kind of what they're insinuating here. So we will call this function this way. So you just pass the name of the array. Easy enough, right? Pass the name of the array, that's it. So since we took 2 arguments here, we also have that size that we're taking in. We will pass number of scores, which represents the size, the number of elements in this array. and that's it. Easy enough. Yeah, you don't want to put any index, any size in here. Okay, and for the argument, as I said, you just pass the name of the array. You don't include the subscripts. You don't include the rather the brackets. All right. Formal parameters. So array formal parameter is a placeholder. So when an array is an argument, when you pass an array to a function and use it in a function call, the array is modified. Anything you do to the array elements will maintain itself after you return from the function call. Remember, I said it's like a pass by reference. So that means that you are writing to the memory location and not some sort of temporary variable. We don't pass arrays by value. We pass them by reference. And the reason is mainly, storage overhead. Okay, so yeah, the variables, the individual elements will be changed if you change them inside the function. So yeah, of course the computer understands, it reserves storage for that data type and the number, times the number of elements in that array. And remember, it addresses the array via the first element in the array, the address of the first element in the array. That's the same as the address of the array. So as far as what a function knows about it, all it knows is the type, integer, whatever, blah, 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 and it knows the address of the array. It doesn't know the size. That's why you explicitly have to pass it the size. Well, you don't have to. It is a best practice to pass it the size parameter. That way you're not tied to using arrays. You're not chained to arrays of a particular size only. Yep, this is what I just said. All right. Const. So when we pass a value to a function and we do not want that value to be able to be modified by the function, it is a best practice to declare that in the function declaration as well as in the function definition to declare that argument to be of a constant type. That way, if we inadvertently try to modify the variable inside the function, we get an error. We get a compiler warning, compiler error. Why would we want to do that to ourselves? Well, trust me, debugging can be a real nightmare. You will make life much easier if you avoid shooting yourself in the foot. Okay, remember practice gun safety? Well, go ahead and practice coding safety, please. You don't want to chase your tail simply because of something you could have prevented via good programming practice. So that's all this const does. Const declares variables to be of a constant type. They cannot be modified inside a function. Okay, so you declare a variable to be const in the function definition, in the function declaration, and you also catch it in the function as const in the declaration, in the definition rather. So sometimes you won't want to modify arrays. Remember, arrays are basically passed by reference, so any changes made to them inside the function will change the array elements. So if you don't want to change them, you catch them, you declare, and define them as constant inside the function declaration and definition, respectively. So here's a little gotcha. If you have a function that takes a const parameter and you call another function and pass it that same variable that's of a constant value in the second function or in every nth function, whatever, if you're iteratively calling functions, or even recursively, you will need to declare that as const in those auxiliary functions as well, or else the compiler will give you an error. So here's an example of using a constant. So say we have this is computing the average of an array of doubles. So we have our integer, or excuse me, I'm sorry. Okay, we have an array of integers. And of course, we declare that we pass the size of it as well. We want to compute the average. We compute the average as a double simply because we want to promote the value to a double type so that we don't just end up with an integer. We want a little more precision than that. So we're taking, here we go, we're taking this integer array in, and we don't want to change any of these values, okay? If we want to avoid inadvertently changing these values inside the function, we declare it as const. That way, if we try to write to or change the array in any way, we get an error. It lets us know we did something wrong. We look, we see what we did, and we say, okay, good. You know, we didn't have to test and debug and pull our hair out, figuring out what the problem was. And of course, we just return we return a double value. We don't show the definition of the auxiliary function compute average, but we don't need to. You get the idea here. Okay, now this is a problem. You see why? We have a constant in show difference. However, we are using the same constant parameter to call compute average, and it is not declared as constant in compute average. Trouble, compiler's going to give us an error. We would need to do this. Now, this code will compile. In fact, let's go ahead and take this. We'll leave these as, you know, what we call stubs. We won't really put too much code in there. So we leave that stub there. All right. Just a moment, please. Okay. All right, so we've got our declarations. Notice show difference has constant. Compute average does not have the array declared as constant. So what we'll do, we'll call compute average from within show difference, okay? And we, notice we aren't passing, it's not a constant here in compute average. So let's see what we got. We may need to do a little more work here. A function definition not allowed here. Oh, yes. Sorry, I really messed this up. Okay, sorry, just a moment. All right, so see, I was declaring functions instead of functions. There we go. See? Hey, you declared it as constant. You can't do that. You can't change from a constant to non-constant. Okay, so just a little heads up there. So if we were to change to const in our declaration, then we should, cross fingers, be okay. Undefined reference. Okay, good. Yeah, so anyway, completely different error. So yes, that's what the compiler does. It will save us from ourselves. So returning an array. We can return arrays in an indirect way. Pun intended, maybe you'll get that later, but we can sort of return arrays, we just not directly. All right, so we have, there's a case study here. Break it down into subtasks, as anything you want to have each unit perform its own individual function and be coherent. Actually, we'll go through this real quick. So we have a plastic company that has 4 plants, and your data is going to be entered plant by plant. So you have production. You have production, and what you do is they're wanting you to average the productions on a plant by plant basis, and then round to the nearest 1,000 units. Okay, and for each what we'll do is we'll display a little bar chart, and we won't go ahead and complete this program. That's for you. A lot of this is already done for you, anyways, and you'll basically create a bar chart with 1 asterisk representing 1,000 units. So, in that way you'll see kind of a graph of productivity in a bar chart form. Okay. All right. So you see how they're doing it. They're using an array name production to hold the production of each plant. So production is going to be of the size of the number of plants, right? And then we said we had 4 plants. Okay. So again, to the nearest 1,000 units, display asterisk in a bar. All right, so what we want to do, we're gathering data. It says, hey, we're going to prompt the user, okay, what was the production of plant, this plant number X, plant number 0, 1, 2, or well, plant number 1, 2, 3, 4, which would be array indexes 0, 1, 2, 3 for, week 1, 2, 3, 4, etc. Scale, so that's where we round. And then graph is going to be the output based on the results from scale, which is where we round to the nearest 1,000. Okay, so you pass an array as an argument. Okay, again, best practice to pass the size of the array along with the array. And as I said, the size of the array is going to be the number of plants. And the use of a constant is good, where a number remains the same, you want to use a constant. That way you don't have to hunt it down, change it in a million places. You change it once at the top, that's it. Okay, function declarations, yeah, everything is in display 7.5 below. Okay, so input data for plant number, 1, 2, 3, 4. So what we're going to do, we'll read all the data, read it in from the user for plants 1 through 4, array indexes 0 through 3. You'll sum all the numbers for the individual plants. Then you'll set that particular plant's productivity to the total, and then, that's going to be the sum of the production, and then you'll divide by 1,000 and round. Right, divide by 1,000 because that'll give you an even number, and then you'll round to the nearest, to the nearest whole integer. So for our input data function, here you go. All right, so you see we're taking that integer representing the plants, and we're taking an integer, well, that's an integer array rather, and then we're taking an integer representing the size of the array. okay? In a for loop from 1 up to the plant number, you know, this could be translated as, you know, you can think of it as 0 up to the plant number minus 1, depending on how you want to offset it mentally. Okay, get the production for the plant. We call an auxiliary function to get the total. Get the total of the corresponding plant number in the array, in this array. Okay. Now, you know, as we said before, unit testing. Test your smallest units possible. Okay. Test kind of your base unit and build up from there. See what I mean by this? You go bottom up, you know, get total. Get total is tested, and then input data can be tested because it calls get total. So you want to start from your, you know, your bottom up there. Okay, remember boundary cases. That's all this is reminding you. Scale. So yeah, like I said, scale, you can, an easy way to think of scale, you can divide by 1,000. That will give you your, you know, your number of 1,000 units. And then you can round to the nearest number. We can do this one of two ways. We can divide the production by 1,000, or we can divide by a double so that we don't lose that precision. Because you see, this would simply truncate. Division will truncate. Division of an integer by an integer will truncate the decimal portion. So that's the equivalent of the floor function. It will round down to the nearest integer. And instead, we want to round, you know, down if less than, you know, what, 0.5 in the decimal portion. We want to round up if 0.5 or more. Okay, so that's why not 1,000. We'll divide by 1,000 and we'll round this number, this result. So math functions. Speaking of rounding, a few interesting math functions here. If we include the C math header, see some examples of rounding. All right, so I've declared two doubles, 3.4 and 3.6. 3.4 should round to 3, correct? And 3.6 should round up to 4, right? So let's see what we got. Make sure I did stuff correctly. Okay. Yep, there we go. All right, so really how the round function works is kind of interesting. It uses the floor function. It will add 0.5 to whatever number, then use the floor function, and watch how that works. 3.4 plus 0.5 is 3.9. If I round down to the nearest integer, that's 3. Okay. Now let's look at 3.6. 3.6 plus 0.5 is 4.1. Now if I round down to the nearest integer, that's 4. So just a little interesting behind the scenes how it works here. Yes. So, you know, round uses CMath. Yes. We also, okay, yes, the floor and ceiling. So I'll go ahead and explain floor and ceiling. Floor will round down. That's all floor is. Okay. So we should see what? 3, 4, and then we should see 5, 5. Right? Because we're only rounding down. Yes, 3, 4, 5, 5. Now the opposite of floor is the ceiling the math ceiling function, and that's CEIL. Now we will perform this function on the same values, 5.1 and 5.9. So we should see they'll round up to the next integer value, which is 6. So we should see 3, 4, 5, 5, 6, 6. Yep, 3, 4, 5, 5, 6, 6. Good. So yeah, floor rounds down. Oh yeah, so here's, hey, they have it here. You add half and then you round down. Okay, the opposite of the floor function is the ceiling function. You'll use these eventually, even if they don't look useful right now. Okay, so yeah, again, cases, testing cases. The function graph, really all that is you'll display as many asterisks as there are in your resulting function after dividing by 1,000 and rounding. That's all. You're invited, you're strongly encouraged to look at 7.5 to 7.8. It's a bit much for us to look at right here, but you'll see how they go developing the code. And if you have any questions, please ask. All right, can you write a function for function definition for a function called one more, which has a formal parameter for an array, and increases the value of each array element by 1. So we'll go ahead and do this. So we have, what do we call it, one more? No, that was a function name, formal parameter. Okay, so we'll just have a generic array. I won't declare a size. I'll just say it's 1, 2, 3, 4. Okay, and what is called one more. And it's going to take this integer array. Now, note the next part of the question. Are other formal parameters needed? Well, we do need other parameters, right? How else am I going to know what size this array is, unless I know that I always have arrays of size 4. Okay. We'll go ahead and we want to add 1, right? So we start at 0. We end at what? 1 less than the size of our array, right? And I'll index into the array. That should work. Now I should, here, I'll just go ahead and see out. Let's go ahead and display these. So now instead of 1, 2, 3, 4, I should see output. I should see, what, 2, 3, 4, 5, just a moment. Oh, yeah, that's right, array, and I also need to pass it the size. I can say, what, constant size equals 4. Generally, kind of the standard here is that, constants are uppercase. Oops, sorry. One, 2, 3. All right, just a minute. Let's see what we got here. Oh, is less than size, or is less than or equal to size minus 1. Let's see what we get now. Okay, it looks like I was hasty here. What has, aha. Oh, sorry, just a sec here. Take a look at what I've done. I was just a bit hasty. Oh, yeah, I see it now. As soon as I hit pause here, yeah, I'm using the postfix increment. All right, so we can do this. All right, this satisfies the requirements. Yep. If we want, now this isn't going to modify the values in the array because you see all I'm doing here, I'm displaying them. And if I wanted to, what I can do, if I want to modify the actual array itself, yeah. So this way I can modify the array. And remember, keep in mind that if I try to modify an array with a constant, I shouldn't be allowed to do this. Yeah, there we go. Increment of read-only location. Yep, it's read-only because I declared that as constant. All right. Okay. So yeah, you know, as I said, we can't really box ourselves in too much to static array sizes. There are kind of a couple of solutions. You know, really the ultimate solution is to use dynamic memory and use dynamic arrays. So we can use pointers to determine at runtime, not compile time, the size of the array that we want. We don't know how to do that yet. We'll find out how to do that soon. However, what we can do is we can declare an array that, you know, in our wildest dreams could you know, accommodate the number of elements that we may need. So that's one way, but then you're wasting memory. You have a lot of, you know, gaps in there. So what we're going to go ahead with this idea here. So this, you know, these are partially filled arrays. So what we could do in the case of partially filled arrays, we could, you know, we could not only keep a size parameter, but we could also keep a parameter indicating how many of the array slots are used, starting at the ground, you know, starting at 0 going up. So you see they have here, they're declaring, or they're talking about a number used parameter. So that kind of sort of makes sense. I mean, this is one way of dealing with this limitation that we have now. Okay. Now, the ultimate solution, of course, is to use dynamic arrays. So partially filled arrays will do for now. You know, if you have to kind of use some sort of you know, dynamic solution, as of right now, you can use a very large array and you can use a counter to keep count of how many elements are in that array. Okay, each time you add an element, you increment the counter. That's one way to do it. So constant as argument. This is you know, just mainly for clarity purposes here. Okay, but yes, you can use constants as arguments, not a problem. Searching. All right, good. So there's a PowerPoint on this here this week. So searching, you know, searching and sorting are kind of two of the main computer science problems. So if we want to search, we can do it a couple ways. The easiest way to search, and this is what we're only really going to concern ourselves with for now, this will work with both sorted and non-sorted arrays. You know, if the arrays are in ascending order, descending order, if they're in no order at all, you can just go ahead and search. You can iterate through the whole, you do the whole array, right, looking for the element. And if the element isn't found, you generally return a -1. If it is found, you can return the location of the element. So we'll see, you know, we're talking about searching arrays here, so we'll just go ahead and see a linear search. There are a lot more efficient ways to search, binary generally, and that's on sorted arrays. First you need to sort them. But let's go ahead and see an example. Let's say we have we'll say 8. Ooh. They'll say this array consists of the numbers 8, 9, 10, 11. And we'll go ahead and create our search function. We'll say search. It's going to take an integer array. And it'll take a size, an integer value representing the size of the array also. Oops. If, so for each element, we're going to compare, well, actually, we'll need to pass it a search value, a value search for also. So if, for the particular element, you know, the particular part of the array I'm at, if the particular index value is equal to the value being searched for, then I will just return the location of the element. Okay, this for will execute this block, right, and then go back to the for statement. So anything after this return statement is going to be executed only in case we stepped the whole array without returning. So I can just put my default return -1 here at the end. That way we didn't find anything, because we didn't find anything. So what I can do here, I can search for, I'll search for the array, or the ARR array for, and it's a, you know, size 4. We'll search it for, I don't know, 6, which we know isn't in the array. So we should see -1 displayed first. Then we'll search the ARR array for, I don't know, 11. So then we should see 1, 0, 1, 2, 3. We should see 3 returned, right? Because it's at the 1, 2, 3, 4th location, which will return, that means it's a 4th element, which means the 3rd location in the array. Right, so take a look at this again. Taking the array, I'm taking the size, and I'm taking a search value, okay? Array, size, and then the search value. I'm returning the location at which that particular, an element with that value lies, the first element with that value lies. Here it's going to be -1 because it doesn't exist, and then here it's going to be 0, 1, 2, 3. So I'm counting on this displaying -1 and 3. Let's see if I made any mistakes. It's 50-50. Nope, no mistakes. Okay, and we'll run it. Let's see. Yep. All right, good. So there's an example of it. Just a linear search. Linear searches are good in that you don't have to sort the array first. We have some techniques such as binary search. They require sorted arrays. This will work on an array in or not in any particular order. So all we're doing is looking first to last to look for a match. Return 1, -1 if it's not found. We return the array location if it is found. Okay, so if we look at 710, let's see the way they did it here in display 710. We'll compare with what I did. It uses a while loop to compare elements to a target value. Okay, so it's a, yeah, you know, if you don't want to return the location, we can just return true to say, hey, this element is in the array, or false if it's not. Okay, so let's look at 710, 1 and 2. I'm curious here. All right, so we have, let's see, yep, we array, the size, and the target. That's basically what I did. I just called it array, size, and search val. Okay. Yeah, so you see, instead of just, they did a little more user-friendly than me. So instead of returning -1, they display a message to say, hey, sorry, this isn't in the list. If it's not -1, we know that it's a positive location or 0, representing the index of the array and that it's in the array. And then they say, oh yeah, it's here, it's stored in array position, you know, X, whatever is returned. Okay, and let's take a look at 2. We'll actually see the function. Yeah, here's the auxiliary, here's the search function. So they declared it const. They don't want to modify the array, they're just searching it. And then here's your size, and here's your search value, your value being searched for. So they say, while not found. Okay, so they initially declare Boolean to false. If the target is equal to the index, found is true, so they're setting a Boolean to found and returning. Yeah, so this is a little more maybe convoluted way of doing it. See what we got here versus kind of what we got here, a whole bunch of stuff. So, you kind of have to balance, being concise and being readable, and it's not always clear cut. Okay. All right, sorting an array. Yeah, sorting is one of the more important problems in computer science, and sorting tends to be a lot more complex than searching. Okay, it is a very common task. You don't want to see phone book entries out of order. They do you no good. You probably use database queries all the time that sort for you, and you don't even know it. Okay, and this at the bottom is very true. Many sorting algorithms exist. Some are more efficient than others, and some are much easier to understand. So here's an example selection sort. This looks a lot like insert sort that I have in my PowerPoint. There's a little difference. See if you can find it. So selection sort. Yeah, so selection sort will go from left to right, and it will compare elements. If any are out of place, it swaps them. So it's very similar to insert sort in that way. Insertion sort. All right. So look at display 711 and 712. We'll come down here and look at the graphic. I very strongly encourage you to look at the sorting PowerPoint. It contains a whole lot of visuals here. Yes. So this is kind of sort of the same, sort of graphic that I have in the insertion sort in my PowerPoint. Okay, so what we're doing, we're going through finding the smallest value and swapping constantly. See, swap values. I encourage you to read and understand this code. You don't have to reproduce it on the fly. Bubble sort. So bubble sort will go through the array, and it will go through the array as many times as elements are in the array. So here we go. Here's kind of an example here. Initially, we have an array with 3, 10, 9, 2, and 5. So we'll first look at 3. We'll compare 3 at 10. We don't swap it. Okay? These two are in the correct order. Next, we'll look at 10 and 9. Since 10 and 9 are out of order, we'll swap 10 and 9. Okay, so this will now be 9. This will now be 10. Now over here's 10, so we'll compare 10 and 2. They're out of order, so then I'll put 2 here and 10 over here. Then we'll compare 10 and 5. Since they're out of order, 5 will come down here. 10 will come up here. So you see what we've done with each pass, we put the heaviest element over to the right location. So the heaviest element kind of bubbles up in the array, hence the name. Yeah, here we go. So this is what, you know, basically what you see what we did. So like I said, we'll compare 3 to 10, no swap. Compare 10 to 9, we swap. Then we'll go over to the next two, 9 and 2. We swap 9 and 2 since they're out of order. This will be 2, this will be 9. No, excuse me, sorry, 10 and 9, then 9 and 10, sorry. Then we'll, so here we go. Then we'll compare 10 and 2. We'll swap, so this will now be 2, this will be 10. Then we'll compare 10 and 5, and since they're out of order, we'll swap 5 and 10. Now, note that we're still not in order. We're still not in order. That's because we only did one iteration, right? So all we did was we bubbled the heaviest element up. So what we need to do is one iteration for each element of the array. So since we do n iterations for n elements of the array, our complexity is n squared. In other words, we do n squared comparisons, n times n comparisons. So bubble sort is definitely not efficient. Well, not, you know, when compared to other elements, not efficient. We can do better. And yes, this requires nested loops. Remember, n times n, so we'll have to do a loop inside of a loop for this one. Okay. Read up to 10 letters in an array and write the letters back to the screen in reverse order. This is a good one for you. I leave this to you. Multi-dimensional arrays. So sometimes a simple linear array won't work. So let's say, I think we talked about what grades earlier, or tests earlier. Let's say we want to, let's say, you know, that works for one student, but how about many students? We have to have an array for each student. That's garbage. What we can do, and we'll do a small example here. You know, small examples are best, easiest to understand. We can use two-dimensional arrays. I'll call this a student grade array. So we have, there we go. That's how we declare a two-dimensional array. Single dimension, or the first dimension, second dimension. Okay. Now that means that we have, for each student, we have multiple grades. So this first index here is for the students, and the second index here is for grades. So not only can we index in the student, inside each student we can index into the individual grades. And we'll just kind of declare an example here. This is how we declare explicit values with two-dimensional arrays. Let's say our first student is kind of a stellar person here, stellar student. Our second student is, you know, mediocre, run-of-the-mill, average. And our third student is kind of needs to study harder. So there we go, within brackets and then brackets within brackets. This is how we declare explicit values for multidimensional arrays. So here you go, data type, array name, and then you have your two indexes, first size, second size. And you know, as before, 30 would mean 0 to 29, 100 would mean 0 to 99, addressable, indexable. Here they gave page numbers with the number of characters per page. That's kind of what they're insinuating here. Yep, see, 0 to 29, 0 to 99. So for example, 11 would be the second character of the second page. 29.1 would be the second character of the 30th page. 29.99 would be the 100th character of the 30th page and of the last element. So yeah, page is an array of arrays. Okay, it's an array of 30 100-character arrays, if you want to think of it this way. Okay, so The base type of a multidimensional array must be completely specified, so you have to have your data type, and you have to have all the size of, if it's a two-dimensional array, your second dimension declared. If it's a three-dimensional array, in function function declaration, you have to have the second and third index sizes declared. All index sizes except for the first must be declared in function definition, and you'll get a compiler error if you don't. Okay, so we have grade records for, so this is what I'm talking about. These students, and then for each student you have a certain number of grades. In this case, 4 students, 3 grades per student. So that means 0 to 3 addressable and 0 to 2 addressable for students and grades, respectively. Average scores. We can do this. We'll go ahead and do this. This is a good exercise for us to do. We're very near the end. Bear with me. Okay. What we'll do, we'll calculate the average score for each student. So what we'll need is an auxiliary function here, and we'll make it a void type. We'll actually display, to make things a little simpler, we'll display the average grade per student. So we know here we will need to take an integer student grade array. We'll need the size. Now, this is a two-dimensional array, so we'll need 2 sizes. Size of the first dimension, size of the second dimension. Yeah. It's a void type because I'm not returning anything. I'm doing stuff inside the function. I'm not returning a value. The function could still do stuff, but I won't return a value. So we have students and we have their grades. So we'll use nested loops here. This is ripe for nested loops. It's less than size 1. For each student, we're going to calculate the grade. Okay. Now, inside each student, we will have their grades. I think I'm boxing myself into a corner here, but we'll get out of it. Okay. All right, and so average is going to be total divided by the number, right? So we can say, we'll have to declare a total. We'll have an integer total here that we'll use to sum these. And so we'll say total is going to be the value of the grade, which is going to be, for this particular student, I'm inside the student and I'm inside the grade array for the student. So I'm going to add all the grades for the student. Okay, and then here, for the student, I can say, I should be able to here say student averages, and then it divided by, what is the total divided by, yes, size 2 is going to be the number of grades per student, remember, size 2, and I'll make this a double through promotion. All right, there's a pitfall here. What I'll have to do, I'll have to reset total to 0 because of the way I've coded it here. You know, I haven't thought this out. We're just kind of doing this on the fly so that I don't keep adding to total, right, and get some weird averages over 100%. Okay, average SG. I'll call the average function for my, I'll call it on the two-dimensional array. It's going to students in 3 grades. So I can say something like constant num students, well here, num students equals 3, num number of grades equals 3, and so this may work. Let's see what I've done wrong, if anything. Okay, SG as multidimensional array must have bound. Oh, yes, remember I said, okay, we must declare declaration. Yeah, my declaration has to have for other than the, you know, anything other than the first index, I have to have a size declared there. Right, so now let's see what we got. More stuff. Okay, declaration of SG is multi must have bounds. Where am I? SG. Oh, yes. Yes. All right, and let's see what we got. All right, good. This looks correct to me. So I got, oh, sorry. All right, so I got 99, right? Remember we said we had our stellar student. I can look at this and tell you this is pretty much correct. Actually, what I need to do if I want to kind of promote, I can do this. So we got 99. Student 1's average is 75, 80, 70, 75. Yep, that is true. And student 2's average is 55. I can tell that this is true. 50 plus 60 plus 55 divided by 3. I can tell the average is 55, and this is correct. So this is an example of using two-dimensional arrays in functions. And believe this concludes this lesson. Yeah. So you have a little exercise here. Well, you know, write code that will fill the array A below with numbers typed to the keyboard. This should be easy enough for you. You use CN statements. Remember, when you pass arrays into functions, you can write directly to them. And in fact, you don't even need to. Really, the specifications don't include any function here, so you can probably really do it from within the main. Okay. All right. So this kind of concludes this lesson here. See you in the next lesson.